This is a penny, and soon their use in the US will go extinct. So some stores like Aldi and ShopRite are already phasing out the use of the penny, and they're coming up with systems to deal with that. But the question is, are systems like this actually fair to the customer and the store? This is what we want to mathematically analyze.
$56 million a year.
We're not getting rid of the penny. We're discontinuing the production of it.
Though for some businesses, not making sense doesn't make sense. Some retailers are already seeing penny shortages and trying to figure out how to handle cash payments, which make up 17% of all transactions at Quick Trip convenience stores.
Here at Quick Trip, for the favor of our customers, we decided to round down for every transaction. That will cost us this year $3 million.
How do you feel about that?
Well, we wish there was a better option, but we have to do it for the sake of our customers. We didn't want to cheat them out of a single penny.
Would the stores actually be cheating the customers out of a lot of money? And perhaps there is a better way. What about that system in ShopRite? This is why we need to learn how to think critically. This is why we need to do mathematics properly in school. I mean, $3 million is a lot of money. So perhaps there's a better way for it to be fair for the customer and fair for the store without losing all that money. So what's the worst case scenario? The worst case scenario for the store is to lose millions. But what's the worst case scenario for the customer? In order to answer this question, we need only look at the last digit of the change, otherwise known as the pennies digit. So you can analyze each case and look at how many pennies come from each digit. And if you do that, you see that 4 and 9 produce the most amount of pennies. They each produce 4 pennies. Say your grocery bill is $98.11, which is all too common nowadays, and you hand the cashier a $100 bill. Then you get back $1.89 in change. So let's say you go to the store and you get back $1.89 in change. Now all that matters is the digit here. So how do you give back 9 cents? Well, you have 4 pennies. And you have 1 nickel. 5 plus 4 equals 9 cents. Now the thing is, since the stores are not carrying the pennies anymore, you're not going to get 4 cents back. So you'll lose 4 cents in one shopping trip. So that's the worst case scenario. That's the maximum you can lose. Let's do a calculation to try to put this into perspective. Say you make an average of 1 grocery trip per week. Since there are 52 weeks in a year, worst case scenario, you lose 4 cents a week times 52 weeks equals only $2.08 per year. Alright, so to even begin to argue why the penny scheme is fair, we first need to go over some basic probability. So for the case of a discrete finite number of events, we have that the probability of an event X occurring is the number of favorable outcomes divided by the total number of equally likely outcomes. And associated with any probability space is something called the sample space. The sample space is quite simply the set of all possible outcomes, or the list of all possible outcomes. So X will represent the event of getting one of the 10 digits 0 through 9 on the last digit of the total of your grocery receipt. So how do we find the cardinality of the sample space, or the number of elements or numbers in the set? Well, we could just count 1, 2, 3, 4, 5, and so on. But what if there's thousands or millions of numbers? How can we quickly find out how many elements are in the set if it's an ordered list like that? Well, we have to know basic combinatorics. And here's a great book by Ivan Neven, The Mathematics of Choice, The Art of Counting Without Counting. So it's just the last number minus the first number plus 1. So 9 minus 0 plus 1. If the list of numbers only differs by 1. So let's do a quick example. What's the probability of getting a 2 as the last digit in your receipt? Well, there's only one favorable outcome, which is 2. And there's 10 total possible equally likely outcomes. So that's 1 divided by 10, or 10%. There's a 10% chance of getting a 2 as the last digit. Now, of course, the same logic holds for any of the numbers in the sample space. So the probability of getting any of the digits is the same, 1/10 or 10%. All right, So now here's the key idea for the crux of our argument for why the penny scheme given by these stores like ShopRite should be fair. What we'd like is some type of measure, or to be able to do some type of computation to show that the win or loss values of the customer or the store is zero. In other words, over the long average, as time goes to infinity, or the number of trials goes to infinity, the average win-loss value is net zero. And in probability theory, this is exactly what we call the expected value. So let's do a simple example of calculating expected value for a fair die. So one die is a cube, it has 6 faces, there's 6 numbers on it, or 6 different arrangements of dots, 1 through 6. What is the expected value if you roll the die an infinite number of times? What would be the average long run expected value that you would get? So we define the expected value as the sum over the sample space of the probability of each event occurring times that event, where the event is given a numerical value. So of course, an event could be a color. You could grab a colored ball out of a bag, but ultimately you have to assign some type of number to that color. So the probability of rolling any one of the 6 numbers is just 1 over 6. So you compute the expected value, it just turns out to be the average number of the set. 1 plus 2 plus 3 plus 4 plus 5 plus 6, all divided by 6 is just the mean or the average value, which comes out to 3.5. What you see is 3.5 is not part of the sample space. So sometimes that can happen with the expected value. Alright, so let's try to construct a specific example to get a feel for the rounding scheme. Now on the poster on the left, it says they're rounding your change, but they're actually rounding your balance first. But it doesn't matter, it's symmetric. Whether you round the balance first or the change, it gives the same effect, it's symmetric. So a lot of times in mathematics, to solve problems, it's helpful to create a table. So suppose you spend $98 in change at the grocery store. Then you get some amount of change back, it gets rounded, and then we can compute the win or loss value. Now first notice, we've made the table such that the win or loss value is from the customer's perspective, not the store's perspective. But again, it's symmetric. So this table contains a list of all possible cases that can occur at the grocery store. So let's go through some of them. So say you spend $98.10 at the store. Your change will be $1.90. Since that ends in a 0, there is no rounding, so the customer doesn't win or lose anything. They win or lose 0 cents. Say you spend $98.11 at the store. Then your change will be $1.89. Since the last digit ends in a 9, that's going to be rounded up to the nearest 10. So that's $1.90. So that means the customer wins 1 cent. And similarly, if you spend $98.12, your change will be $1.88. Since the last digit ends in an 8, again, that will be rounded to the nearest 10, which is $1.90. So this time the customer wins 2 cents. If you spend $98.13, your change is $1.87. Now, since the last digit ends in a 7, that gets rounded down to $1.85. So the customer loses 2 cents. $98.14, the change is $1.86. That gets rounded down to $1.85. The customer loses 1 cent, and the cycle begins again. So you can see that the table is symmetric, 0 through 4, and then 5 through 9 as the last digit. And now we see that the last column forms our sample space of events, but all the elements are doubled up, and the sample space is a set, so we can't have redundant elements. So we'll just take the 5 unique elements, and then double up the probabilities. And we see that for each event, the probability is the same, 1/10. So now let's actually calculate the expected value of our random variable x, which represents the win-loss values in cents. Now again, the logic goes as follows. In order for the scheme to be fair, the win-loss value should come out to be 0, which means the expected value should come out to be 0. Each element in the sample space has a probability of 2/10 or 1/5, so we could just bring that outside the sum, and then when we do the sum of the elements, they all cancel out, and we're just left with 0. So the expected value is 0. And this demonstrates that the rounding scheme that ShopRite came up with is fair for both the customer and the store. Here's a visual animation of the expected value as the long run average value. You see that as the number of trials grows and grows, the average value converges to 0, which is the expected value. It's amazing how many problems could be solved by modeling them as a continuous flow. Now you might be wondering, with over 150 billion pennies in circulation in the economy, why do we need to phase out the use of the penny? Why would there be penny shortages? The faucet was officially shut off on November 12, 2025 at the Philadelphia Mint. See, if we shut off the flow of pennies into the economy, there's essentially only a one-way flow from the store to the customer. Okay, so here we have the penny circulation animation diagram for the economy. So we have the stores, we have the customers, we have the banks. So the stores start out with a bunch of change, pennies, to give back to the customers when the customer buys something. So say a customer goes into the store and buys something with cash. The store might give back some change, which might contain some pennies. So there's a directional flow from the store to the customers of pennies. And now the customers have pennies and have other change. And maybe they want to wrap it up and get actually cash dollars for it from the bank. The only issue is this process is very slow. People are not efficient in doing this. I mean, they could have change in a piggy bank for years. They could have change in their couch for years. They could have change sitting in a jar for years. But the stores need it now each day for the customers. So it's a very slow process for the pennies to make their way from the customers to the bank. And then even once the bank has pennies, change, it's just too expensive to redistribute back to the stores. It's too heavy to transport. So this penny circulation animation diagram shows why, even though there's over 150 billion pennies in circulation, once you shut off the faucet, once you shut off the production of pennies, reserves will eventually run short. Reserves will eventually vanish. And of course, if a customer buys something at a store, rarely, if ever, like never, they're going to give back penny change in cash back to the store. So this demonstrates that there's only a one-directional flow of pennies from the store to the customer, but the store is not being replenished. Therefore, the store reserves are going to run out at some point. So this is why the stores need to phase out the use of the penny and come up with an alternate system to deal with this. Okay, so we went into the question, is the last digit truly random? When you look in stores, especially grocery stores, the prices of most products end in a 9. So like $3.49 or $1.99. Or they might end in a 5, like $2.95. So most products end in a 9 or a 5. The pennies digit is one of those two. So it makes us a little suspicious. Is the last digit truly random? Well, the other thing is you're going to multiply by the sales tax, which is in New Jersey 6.625%. Okay, so when you sum over the products you buy and then multiply by the sales tax, what do you think? Pause the video to think about this before I reveal the answer. So it does act as a multiplier. So all of this summing over the products and then multiplying by the sales tax acts as a randomizer. All right, so we already talked about how the US government is losing a huge amount of money producing and distributing the penny. In fact, it costs 3.69 cents to just produce and distribute one single penny. That's a huge loss. Now let's turn our attention to the nickel. Are we breaking even with the nickel? Or are we losing money with the nickel? Or are we making a profit? Well, it turns out we're also losing money with the nickel as well. In fact, it costs 13.78 cents to produce and distribute a single nickel. That's almost 3 times its value. So the US government is also losing a lot of money with the nickel. So here's a question. If we were to also phase out the nickel, could we come up with a similar strategy as we did with the penny so that stores and customers would be fair in their win-loss values? So take some time to think about that. So as usual, intuition is very important. In fact, it's critical. But at the end of the day, it has to be backed up by formalization. So when you write down this scheme for the nickel and you analyze it, you actually find something very interesting. I think I'm going to have to do another video on analyzing the scheme for the nickel. But let's just say maybe it's not what you would expect. See if you can analyze this nickel scheme, or try coming up with another one that you think works. And when you do this analysis, then you'll realize why the US nor Canada has attempted to phase out the use of the nickel despite losing millions and millions of dollars on it. Alright, so you're probably wondering about the other 3 US coins, the dime, the quarter, and the half dollar. Well, it turns out they're all profitable for the US Treasury, the government. This term is known as synergage. So for example, the dime costs 5.76 cents to produce and distribute. This creates a yearly profit of over $125 million. The quarter costs about 14.68 cents to produce and distribute, collecting $300 million in yearly profits. And the half dollar costs about 34 cents to produce and distribute, collecting a yearly profit of $8.4 million yearly for the US government. Now this video is primarily about the mathematics of the coins, but you might be wondering why the cost difference, why some coins create profit while other coins lose money. Well, a large part of it, as you might imagine, has to do with the materials the coins are made out of. It could be a fun project for you to look up. What is the penny made of? What is the nickel made of? Why are some of the coins profitable in terms of their material science and some are not? You know, that could be a good project to do in school. Okay, so I just want to show you that you can add the probabilities and get 1/5. So suppose we have 2 independent, mutually exclusive events, A and B. Now this part here about being mutually exclusive is critical, okay? Then the probability of A or B occurring is equal to, learning isn't linear. Sometimes we make mistakes. It's not a mistake, it's just want to go to the next line. So the probability of A or B is equal to the probability of A union B, which is equal to the probability of A plus the probability of B occurring. So mutually exclusive, there's actually, in the general formula for the probability of A union B, there's another term here, but that becomes 0 because there's no intersection. So for example, what's the probability of getting a 1 or a 6 digit on your receipt? Well, that's just going to be the probability of getting a 1 digit plus the probability of getting a 6 digit on your receipt. And of course this holds because you can't get both at the same time. They're mutually exclusive events. And so they both have a probability of 1/10. So we can just add them. So that's equal to 2/10. And 2/10 is 1/5 or 20%. Now, this also shows that we can also partition the integer 0 to 9 in another way by the win-loss values. So S1 is 0 to 5, we don't round. That's 0 cent loss. S2 is going to be 1 and 6. That creates a 1 cent net gain. S3, that's going to be 2 and 7. That creates a 2 cent net gain. And then S4 is going to be 3 and 8. That's going to create a negative 2 net loss. And then S5 is going to be 4 and 9. And that creates a negative 1 net loss. Okay. Some stores like Aldi and ShopRite are already phasing out the use of the penny. See a penny, pick it up, and all day you'll have good luck. Heads or tails? It's tails. Thanks for watching my video. Who knew the humble penny could be so interesting? I've included the Desmos program links in the description below. If you found this video valuable, please consider liking, subscribing, and sharing. And please check out my website for all your math resource learning needs.